Hi y'all, let's jump right in. This one looks fairly standard, but some interesting things are going to come up. So the first thing that we need to do, our goal here is to sketch this rational function, is to get the numerator and the denominator both fully factored. So the numerator is a difference of squares. It will factor into an x plus 2 times x minus 2. The denominator sometimes throws people off, but it's actually one of our easy ones. We can factor out a greatest common factor of x. So factor out an x and you're left with an x minus 2. And here's where we can see that it's going to get interesting. What jumps out at me is I want my algebra brain to take over and say, okay, I see the same factor top and bottom. Everything's fully factored out, so it's legal to go ahead and start canceling. But here's where we have to get a little bit more clever than just our algebra level thinking. This is our functions level pre-calculus thinking, and we have to think about, is it really true that that just goes away? So what I'm wanting to say is that function k of x is actually identical to x plus 2 over x, this simplified version, but this is a question mark still, so we want to think about it. It turns out that the answer is it's really close. The only difference between these two functions is that you cannot plug, here we'll even go right back here. In the original function, you cannot plug 2 in. If you plug in 2, you get 4 minus 4, which is 0 on the top, and you get 4 minus 4, which is 0 on the bottom, and 0 over 0 is undefined. Even if the top is also 0, you're never allowed to have 0 in the bottom. So this function is undefined at x equals, what did we say, positive 2. I have to think about it for a second. Whereas over here, if I plug in positive 2, I get 4 over 2 equals 2. Works just fine. Anything else you plug in, it's not going to matter whether you use the original form of this function or the middle factored version or the final version. So for example, if I plug in, let's say I plug in x equals 5, I'm going to get a 7, sorry, that's hard to read, a 3, what did I say I was plugging in? 5, and 3. And notice the 3's really will cancel. The only thing that won't cancel out is a 0 over 0. You can't really technically cancel it out. It's still undefined. So what we can say is that this equality in the middle holds. I can erase the question mark as long as I keep track of the fact that there was a domain problem in the original function. So when you cancel out a factor, it actually does leave one discontinuity in the graph if you want it to be truly the same function. Okay, so what we just discovered was a hole in the graph. So we're going to say, yes, we can use this simplified version, but we have to keep track of the fact that on our list, zeros, vertical asymptotes, holes, x equals 2 is a hole in the graph. And it's really handy to know not just the x value, but also the y coordinate of that hole. And the way you get that is by just plugging back into the simplified version. So basically what we say is we know there's going to be a hole in the graph, but the y value should match up exactly with this new function that we've simplified down to. So even though we're not going to put a point there, we can plug into that simplified version and say, okay, what did I have? 4 over 2, which is 2. Lots of 2's floating around in here. So put a little star by this. A lot of people forget this. To find the y coordinate of a hole, you need to simplify the rational function and then plug in its x coordinate. So plug it into your simplified version. I try always to look for the hole first because it will hopefully remind me to not include x equals 2 as an x-intercept or a vertical asymptote. It is neither of those. It is actually a hole in a graph. So now that we've got this simplified version, we can use it to get our zeros and vertical asymptotes. To get zeros, we want to know when does the top equal 0, and that happens if x is negative 2. So we have one x-intercept at negative 2. For vertical asymptotes, we want to know when the bottom is 0, and that happens if x equals 0. So again, zeros are points, holes are like points on the graph as well. Vertical asymptotes are actually vertical lines. We can also use the simplified version to get our global behavior. So the only thing you need to remember for the unsimplified version is that that is where you figured out that there was a hole instead of either an asymptote or a zero. So global behavior, if we look at this final version, and you could look back at the original fraction, it would give you the same answer. What I'm seeing is that the power on x is 1 in the top and 1 in the bottom. So that ties, which means I'm going to look out at what's my leading coefficient. It's 1, which makes me say that the graph will have a horizontal asymptote at y equals 1. And again, remember the thinking there is your global behavior is what happens as x goes to plus or minus infinity. Really, really, really big x values. So if we're looking back at our fraction, I would say, okay, if I plug in 1,000,000, 10 to the 6, top and bottom, I have 1,002 over 1,000,000. That's really close to 1. If I plug in 1,000,000,000, it's going to be closer to 1. If I plug in 1,000,000,000,000, it's going to be even closer. So that's your global behavior. So finally, we get to see one with a hole in the graph. Let's plot out our information. We have an intercept at -2. We have a vertical asymptote right along the y-axis. Always draw these in with the dashed line and label them for me. I need to know exactly where they are. We have a horizontal asymptote at y equals 1. And last one, we have a hole in the graph at 2, 2. So the hole is just an open circle saying we can plug in anything as close as we want to this point, but we can't plug in exactly 2. If you plug in exactly 2, you get a domain problem. Technology will not show you that hole in the graph. You have to know to look for that. So don't trust a Desmos or anything like that. If you know exactly where to look, you can type in exactly 2, or if you can click on exactly 2, technology will usually tell you there's no y value, but it won't put the marker there, so you won't be able to see it unless you know to look for it. Okay, so that's all of my local behavior. My global behavior tells me to start right near this horizontal asymptote. And the first piece of local behavior I have is this x-intercept. So I'm just going to head down to that. Sometimes when you check graphs, you'll see that they actually maybe will start above the asymptote sometimes and then jump and cross down. There's no way for us to tell that without technology or calculus. So we're happy with the general shape of knowing it should be near that and then come down and cross. And it is in fact cross. If we look back at our factors, you can look at any version of this. Everything's multiplicity 1, so there's not going to be anything weird happening. We are going to cross straight through, and the next piece of local behavior is the vertical asymptote. So our options are continue down to -infinity or turn around and go up to +infinity. And we actually don't really have the second option because there is no x-intercept. I'm not allowed to cross the axis again, so I will be forced down to -infinity. The asymptote also had a power of 1 on it, that factor of x in the denominator, which means it will change signs. We will switch from negative to positive values for that factor, so our y values will switch. And then the next piece of local behavior is the hole in the graph. And a hole in the graph basically acts like just a single point. You treat it just like a point. We have to go through that point, and then we will get drawn down towards our horizontal asymptote, and that will be our graph. So what we've really said here is our graph looks exactly like x plus 2 over x, except that we have to draw that single hole at 2, 2. And I think you'll even see some where it simplifies down and it's not even a fraction anymore. A rational function could just be a straight line with a hole in it, or a parabola with a hole in it, or anything like that. So sometimes there is no vertical asymptote, and instead you'll have a hole in the graph. Sometimes you don't have either of those, but most of the time we have some combination of vertical asymptotes and holes in the graph.